All right, welcome everybody. I just wanted to give an introduction today to polytopes and how they appear in linear programming. This is from a very high level. And in particular, I wanted to talk about cubes and cross-polytopes. These are two canonical types of polytopes that everybody should know about. I'm guessing most of you have heard of cubes before. Many of you probably haven't heard of cross-polytopes, but they're super important, almost equally as important as cubes, and I want to introduce you to them. So in linear programming, we're trying to optimize a function subject to some constraints, and here I've listed 5 constraints. In my picture, I've drawn really 7 constraints, and that's the extra dots here. But my 5 constraints are that the x1 coordinate has to be non-negative, so I'm on this side of that line, and the x2 coordinate is non-negative, so I'm above this horizontal axis, and negative x1 plus x2 is at most 1, so I'm below that line, and x1 plus 6x2 is at most 15, so I'm below this line, and 4x1 minus x2 is at most 10, so I'm to the left of this line. I didn't write them down, but pretend I also have this constraint. I have to be below that line, and I also have this constraint. I have to be to the left of that line. All right, so these are a collection of half spaces. Each constraint gave me a half space. So in particular, this constraint gave me, this half space. Half of space has been cut out by that constraint. And if I take the intersection of all of those half spaces, I get this feasible region or convex polyhedron. Okay. It includes the interior. I should have drawn that. Notice that you might have constraints that don't give you that don't actually touch your polyhedron, right? So here are constraints that are sort of redundant. They're redundant in the sense that they're implied by the other constraints, but you might not know that in advance, right? If I give you 100 constraints, that doesn't mean you have a polyhedron with 100 faces. You might only have 3 faces, and 97 of your constraints were not needed, and only 3 of your constraints were needed, something like that. Okay, so a convex polyhedron is an intersection of finitely many closed half spaces in Euclidean space. Each of these is a closed half space, and we're taking their intersection to get this convex polyhedron in blue. Later, I'll just define what it means for a shape to be convex or not, but that's not the point today. A convex polytope is a bounded convex polyhedron. So if you're a math grad student, you probably know what bounded means. If not, let me just tell you sort of informally out loud what it means for a shape to be bounded. So a shape in Euclidean space is bounded if you can find a ball that's large enough so that your ball contains the shape. Okay, so here I found a ball. It has a finite radius. Maybe let me try to draw the center of the ball a little bit closer to the center. Okay, I found some ball that has a finite radius, and the ball contains my polyhedron, and so therefore my polyhedron is bounded. So it just doesn't go off to infinity. So convex polytope is a bounded convex polyhedron. Personally, in my speech, I don't think I'm very careful about using polyhedron versus polytope. I think people who are in convex geometry are careful about that. So polyhedrons are just intersections of half spaces. They might be bounded or not. Polytopes just imply that they're furthermore bounded. As an example, if I looked at this half space, so everything to that side, that's a polyhedron that's not a polytope because it's unbounded. But the blue region is a polyhedron that is also a polytope because it's bounded. Okay, I've called definition one, because there's a second equivalent definition of convex polytopes, bounded convex polyhedra. Equivalently, a convex polytope is the convex hull of a finite set of points in Euclidean space. This blue polytope is the convex hull of these 5 points. I won't rigorously define convex hull. If you wanted a rigorous definition, it's the intersection of all convex sets containing a set of points. Okay, let me give you an intuitive definition. Here I have a set of points in the plane, 5 points. To find the convex hull, just put a rubber band around all of your points, okay? And then what do rubber bands do? They shrink. So this rubber band shrinks, and as this rubber band shrinks, it eventually snaps into place right here, okay? And, whoops. Once your rubber band snaps into place, your rubber band has outlined the convex hull. I could do that even if I had more points. I could give you this larger set of points, and I could ask, what's the convex hull of this larger set of points? So I put a rubber band around, and then I let this rubber band snap down. I still get the same convex hull. Okay. So the convex hull of these new 11 red points happen to be the same as the convex hull of my original 5 points. I'm drawing my pictures in the plane, but you have analogs of all this in 3D and 4D. You know, so in 3D, if I wanted to take the convex hull of a set of points in 3D, I would surround them with a rubber balloon, and then I would let the rubber balloon snap. All right, so by definition one, we can define some shapes. We take intersections of half spaces, and we require that the intersection is bounded. Okay, we get a set of shapes. By definition two, we can define a set of shapes. We take arbitrary finite collections of points and we take their convex hulls. It turns out that those two classes of shapes are the same, okay? So any convex polytope that you can obtain by definition one is also a convex polytope that you can obtain by definition two, and vice versa. Intuitively, you know, maybe it seems unsurprising to you that you get the same set of shapes by either taking intersections of half spaces or taking convex hulls of points. But it takes some work to prove that. So that's a theorem. It's a theorem that these two definitions are equivalent. It's called the Minkowski-Weil theorem. You know, one of them proved that any shape obtainable by definition one can be obtainable by definition two, and the other proved the opposite. And I think this was done like between 100 and 200 years ago. So it's old and well known, but it's not super easy. This wasn't known to the Greeks, for example. It's harder to prove this than you might think. I don't know how to prove it off the top of my head. I'd have to look at the book. Questions so far? All right. Given a convex polytope described as half spaces, it's not always easy to find the vertices. So pretend I gave you these 7 constraints, you know, including this one and this one. It's not so easy to find the vertices of your polytope, right? Because you might have to, like, you know, check these other possible vertices, you know, are those vertices of your polytope? Similarly, given a convex polytope defined via vertices, so let's say I have 11 vertices, and I ask for a polytope that's defined as the convex hull of those vertices, it's not so easy to find the half spaces, right? So the half spaces are these, right? but you have to rule out this guy being a half space, or you have to rule out this one being a relevant half space, or this one. So good algorithms exist to go from the half spaces to the vertices, or to go from the vertices to the half spaces, but they scale poorly with the dimension of Euclidean space. So as you get into higher and higher dimensional Euclidean space, these algorithms get worse and worse. So yeah, you can definitely go from one to another on a computer. There's good software for this, but the running times of those algorithms scale poorly with the number of points in the dimensions. Okay, so I want to finish by describing cubes and cross-polytopes. And cubes and cross-polytopes will be related to the fact that it's sometimes hard to go from the faces to the vertices, or to go from the vertices to the faces. All right, so the two-dimensional cube is just the square. The three-dimensional cube, we all know. The one-dimensional cube is just a line segment. Let me try to draw for you a four-dimensional cube. So it's living in 4D, so I can't make it fully realistic. But to draw the 4D cube, you can just draw two 3D cubes and then connect them. Oh boy. All right, so I've drawn two 3D cubes, and then I just connect them to get the 4D cube. That is actually how I went from the 2D cube to the 3D cube, right? To get from the 2D cube to the 3D cube, I just drew two different 2D cubes, and then I connected them. And that is actually how I got from the 1D cube to the 2D cube. I just drew two different 1D cubes and then connected them. Okay, so when we see this iterative procedure, we can start to count the number of vertices and faces of these cubes. So the 2D cube has 4 vertices, 1, 2, 3, 4, and it has 4 faces, 1, 2, 3, 4. The 3D cube has 8 vertices and 6 faces. 1D cube has 2 vertices there and 2 faces. Same thing. In this example, the faces are the vertices. The 4D cube has 16 vertices. I can count those. It's a little hard to count the number of faces, but it should be 8 faces. One of the faces is this 3D cube. Another face is that 3D cube, but then I have other 3D cubes. You know, I have a 3D cube here that's a face.
So when you say faces, you mean n-1 dimensional things?
Yeah, so let's put it this way. We're living in the line, the plane, 3D, 4D, and ND. And faces in n dimensions, face is going to be an n-1 dimensional polytope, you know, that's on the boundary of this cube. It's the rigorous definition would be it'd be the intersection of this cube with a supporting half plane. You know, and then that would be a face. And I guess we're looking at n-1 dimensional faces. Yeah. Good point. So maybe I should say that faces, I really mean top dimensional faces. Or, okay, I should say n-1 dimensional faces. How about that? Okay, ND cube. How many vertices do you think we have? Come on, you all are making me look bad on YouTube right now.
2 to the n?
2 to the n, yeah. And how many faces do you think you have?
2 times n.
2 times n. Yep. I would say it's easier to count the number of vertices, right? Because we're always just doubling the object, right? So here, this one's easier to count. For me, this one's just a little bit more pattern matching. And so the cube has exponentially many vertices in terms of the number of faces. So you can have exponentially many vertices in terms of your number of faces. So this is telling you that if I give you an arbitrary polytope and it has some number of faces, some number of constraints, you might have exponentially many more vertices, right? This is why it's not easy to go from a polytope described as half spaces to one described as the convex hull of vertices, right? Because you might have exponentially many vertices in terms of the number of faces, right? So you're not going to expect a polynomial time algorithm because the input, might be linear in n, but the output is exponential in n. Do you see that? Okay, so I should have given myself more space, but this is why we expect, hard to go from the faces of the polytope to the vertices. I'm not saying it's hard in the cube, but I'm just saying you should expect it to be hard for an arbitrary polytope to go from faces to vertices, because you can have exponentially many vertices in terms of the number of faces. Okay, cross-polytope. You are less familiar with cross-polytopes, I'm guessing, but that's okay. I won't really write down a rigorous definition of cross-polytopes. You can look it up on Wikipedia, but let me say it out loud and give you the basic idea. Okay, so what you do for the cross-polytope is, here's our 2D example. Goodness. Wah, wah. Those are supposed to be the coordinate axes. Okay, so you look at your standard basis vectors in 2D, and then you also consider their negatives. What you do is you take the standard basis vectors and their negatives, and the cross-polytope is defined as the convex hull of the standard basis vectors and their negatives in n-dimensional Euclidean space. So in 3D, I have 3 coordinate axes. Wow. Oh boy. All right, I have 3 coordinate axes. I have 3 standard basis vectors, and then I also consider their negatives. Okay. And I take the convex hull of those, in this case, 6 points, and I get the cross-polytope. So let's count the number of vertices and faces. You should already know the number of vertices. It's 2n, because I defined it as an ND. I have n standard basis vectors. Along with their negatives, I have 2n vertices. And then when I take the convex hull, they all turn out to be vertices. So the number of vertices is 2, 4, 8, 2, 4, 6, 8, all the way up to 2n. Number of faces, here I have 2 faces. In the diamond, I have 4 faces, 1, 2, 3, 4. In the, this is an octahedron. In the octahedron, I have 8 faces. So 4 triangles on top, and then 4 triangles on bottom. Okay. So let me try to draw the 4-dimensional cross-polytope. Oh boy. Why do I set myself up for failure? I have my x-coordinate, my y-coordinate, my z-coordinate, and then in 4D, I also have my w-coordinate. Okay, so now I take the standard basis vectors and their negatives. Okay. Let me start just with the 3D picture. Okay. I should have done that in a different color. Let me try again. Okay. So I start just with the 3D picture. It's pretty good. To draw the 4D picture, let me first go from 2D to 3D and 3D to 4D. Okay. What we're doing here to go from one dimension to another is we're doing an operation called a suspension. So, and you start with your 1D cross-polytope. What you do is you take that, you add a point above and below, and you suspend it. So you connect every point from what you had before to the top point, and you take every point from what you had below to the bottom point. Okay. So in 2D, what we had was the square, and then you suspend it by adding a point above and below and connecting everything to the new bottom point, coning over the top and coning over the bottom. All right. So if I wanted to draw this 4D cross-polytope, I'm going to get rid of my w-axis and maybe put it somewhere else. Here's my w-axis. What I do is I add a cone point above and a cone point below. And then in 4D, I'm forming this cone over this 3D shape. So in 4D, I'm sort of forming this cone over a 3D shape, a cone from below, and I also have this cone from above. All right. I enjoyed that. I apologize if you didn't. So it's not so easy to see the number of faces, but it turns out to be 16. And the number of faces is 2 to the power n. And so the cross-polytope has exponentially many faces in terms of the number of vertices. And therefore, you should expect that for polytopes, it's hard to go from the vertices to the faces. I might write down just, 100 vertices, and I take the convex hull, and I get something that's exponential in terms of the number of vertices, 100, as my number of faces. So you don't expect a polynomial time algorithm to have 100 as input, and something exponential in terms of 100 as output. Let me end this video just by explaining the comment that cubes and cross-polytopes are dual to one another. It's no surprise that these formulas for vertices and faces just got flip-flopped. Okay, these shapes are dual. And what does that mean? So I'll draw my picture in 2D first. The dual object of this 2D cube is obtained as follows. For each face, put a vertex. And then whenever two faces intersect, draw an edge. Okay. And what did we get? We got the two-dimensional cross-polytope. Similarly, take the dual of the two-dimensional cross-polytope. For each face, put a vertex. And whenever two faces intersect, draw an edge. And we get the two-dimensional cube. Similarly, let's go from the 3D cube and take its dual. So for each face, we put a vertex. We have a vertex on top, a vertex on bottom, on right, on left, in front, and in the back. Okay. And then whenever two faces intersect, draw this edge. So the bottom face intersects the left, the front, the right, and the back. And then the top face intersects the same. And we have these intersections as well. Okay. So when I take the dual of the cube, I just get the octahedron, the cross-polytope. And vice versa. Let's take the dual of this octahedron. This drawing's not going to be very good, but you can see I have, 4 vertices on top, 4 vertices on bottom, coming from the 4 faces. And then when I connect them up, I think I did that right, you get this cube. Okay, so this dual operation sort of clarifies a little bit why the formulas for the number of vertices and the number of faces have swapped. Because when you take the dual, you're replacing each face with a vertex and vice versa.
A quick question for you on that.
Yeah.
Is the Jacobian 1 on an operation like that, or is it going to not conserve area?
Oh, I see.
Volume, conserve volume might be better.
Yeah, I think we're changing volumes. Yeah, I'm not trying to make any statement about the volumes.
I was just curious. It seemed interesting.
Yeah. Let's see. So, it sort of depends on where you define these vertices to be. But this is more combinatorial operation. All right, so let me wrap up this video. That was my excuse to teach you about cross-polytopes. They're dual to the cubes. Cubes have exponentially many vertices in terms of the number of faces. And so the dual objects, the cross-polytopes, have exponentially many faces in terms of the number of vertices. So, thanks. Hey, everybody. I just wanted to give an addendum on cubes and cross-polytopes. So I explained last time how the cube has 2 to the n vertices. So we go from 2 vertices for the 1D cube to 4 vertices for the square to 8 vertices for the 3D cube, etc. I did a poor job explaining why the cube has 2 times n faces of 1 dimension lower. So, the 2D cube has 4 faces, and the 3D cube has 6 faces. And then I want to draw an arrow from the front and the back. And Anthony pointed out the right way to see this. The linear constraints defining these cubes are as follows. You have 2 linear constraints for each dimension. So in the x direction, we have 2 constraints, and in the y direction, we have 2 constraints. And then once we get up into 3D, we have 2 x constraints, 2 y constraints, and 2 z constraints, the front of the cube and the back of the cube. Do you all see that? Cool. And then I didn't do a good job of explaining why the cross-polytope has as many faces as it does. So we did talk about why the cross-polytope has the prescribed number of vertices. The cross-polytope in dimension n always has 2n vertices, and that's just because you have 2 vertices for each coordinate axis. Okay. Why does it have 2 to the n faces? Let me give you 2 explanations of that. One explanation is that the faces correspond to the quadrants or the octants. So in 2D, the cross-polytope has 4 faces because there are 4 quadrants in the plane. And then in 3D, the cross-polytope has 8 faces, 1 for each octant. Another way of explaining this that Anthony pointed out and that I quite like would be using my suspension description of the cross-polytopes. So I said you could get from one cross-polytope to the next by just suspending. So to go from the interval to the diamond, I suspend the interval, meaning I add a vertex above and below, and then I take the cone over what I had before. And then to get from the diamond to the octahedron, I add a vertex above and below, and then a cone over it. All right, so how do we use this to count the number of faces? Well, we do sort of a proof by induction. Our base case is that the cross-polytope in dimension 1 has 2 faces of dimension 0, 2 vertices. Now when I suspend, I add a vertex above and below, and then this 0-dimensional face in the interval, so here's my interval, and I've circled the 2 0-dimensional faces. This 0-dimensional face becomes a 1-dimensional face in the northern hemisphere, and this 0-dimensional face becomes a 1-dimensional face in the northern hemisphere. And similarly, this 0-dimensional face becomes a 1-dimensional face in the southern hemisphere, and the 0-dimensional face on the right becomes a 1-dimensional face in the southern hemisphere. So each of my prior faces gave me each of my prior 0-dimensional faces gave me 2 1-dimensional faces, one in the northern hemisphere and one in the southern hemisphere. And then I do that again. So let's go from the diamond to the octahedron. The diamond has 4 1-dimensional faces, and I'm going to use that to argue that the octahedron should have 8 2-dimensional faces. So I want to do 4 times 2 is equal to 8. And the reason is going to be, let's draw my 4 1-dimensional faces of the diamond. 1, 2, 3, 4. And then I suspend. I add a vertex on top and on bottom, and then I cone. And then when I cone, this 1-dimensional face gives me 2 triangles, the northern hemisphere triangle and the southern hemisphere triangle. This 1-dimensional face gives me 2 triangles, northern hemisphere, southern hemisphere. This 1-dimensional face gives me 2 triangles in the northern and southern hemispheres. And lastly, this 1-dimensional face gives me 2 triangles in the northern and southern hemispheres. And that process, you can just keep going. If you keep multiplying the number of faces in one dimension by 2, you get the number of faces in the next. And that's why we have 2 to the n faces in dimension n. Questions?